Hi everybody, I hope you're enjoying your cold day so far. Today we're going to start talking about more advanced techniques of integration, and more specifically this video is going to be about U-substitution. U-substitution is one of the 3 more advanced techniques you're going to have to learn. Now when you watch this video, please make sure you're writing down all the notes so that you have everything you need and you're not going to mix up the 3 different techniques that we'll be learning about this week. So far, what you need to realize is that the integration that we've been doing is considered to be more basic and easier. All we've been doing is finding antiderivatives that undo the power rule. So for example, we've been doing things like, if I take the derivative of x cubed, I end up with 3x squared. To go back to where I started by doing the integral of it, all I do is I add 1 to my power, divide by the new power, and I'm back where I started. So that was pretty simple. You're just undoing the power rule. There are many other types of integrals that are a lot messier and more complicated, and they can't be done just by undoing the power rule. You're going to have to undo things like the chain rule and the quotient rule. So here are examples of integrals that you would have to take in Calc BC. This one right here is what we'll be doing this video. It's done using U-substitution. This one will be done using integration by parts. We'll do that this upcoming week. And this one is done using integration with partial fractions or partial fraction decomposition. Again, this video will be doing just U-sub. And the thing about U-sub is it undoes the chain rule. Now, integration by parts undoes the product rule. So let me just tell you something here. Some people, when they look at this integral, they say, oh, that's not that bad to do. All I have to do is take the antiderivative of sine, which is negative cosine, and the antiderivative of cosine, which is sine, and my antiderivative is done. However, if I take the derivative of this, I definitely do not end up back where I started because you have to use the product rule. So integration by parts is more complicated than U-sub. So U-sub is, I guess, the easiest of the 3 complicated ones that we'll be doing. And U-sub is done whenever, like I said, we have to undo the chain rule. And the way that you can tell, just by looking at an integral that you're going to need U-sub, is whenever the integrand has some expression and some form of its derivative in the expression. What's going to happen when you learn all 3 is you might start to mix them up. The key is, look at the integral. It's going to be a little complicated. Look for an expression in it and see if a form of its derivative is also there. That is a dead giveaway for U-sub. We're going to be doing this example first. I'm going to show you how I even got to this integrand, the thing that I'm doing the integral of, so that you can see how exactly this chain rule undoing is done. So what I did is I started with, where's my marker? There we go. I started with the function x squared plus 10, or x squared plus 3 to the 10th, and I did the derivative of it. And as you can see, since I have an inside and an outside function, I had to do the chain rule. I took care of the outside. I didn't touch the inside. I multiplied by the derivative of the inside. So this is what I'm going to do the integral of here, with the hopes of ending up back to my original, and we're going to use U-substitution. All right. So I want you to pause the video and write down these steps here. The reason I have spaces is because in between I'm going to actually write out the steps as I go through the example. So leave spaces in your notes, pause the video, and write all this stuff down, please. That way when you actually listen and go through it, you can just fill in the stuff with me as we go. All right, so you should have your stuff written down as an outline. And we're going to look at this integral here, and we have to pick out U. That's usually the hardest part for people when they get the hang of this. So I want to pick out U so that its derivative is also a part of the integrand somehow. Some hints are U is usually going to be the thing with the higher power. It's sometimes more complicated. Sometimes it's the exponent. It could be in the parentheses. It could be under a square root or a cube root. If I look here, I'm going to use pink for all my U's and yellows for the DU's. I want to look here for the thing that's like on the inside and it has a higher power. Here you can see that x squared plus 3 has the higher power. I know you might be thinking, well, 9's the highest power, but I'll talk about 9 in a moment. And then you want to think, if I did the derivative of my U, I got 2x, is there a form of this derivative here somewhere? And you might be thinking, I don't see 2x, and I don't really either, but I do see 20x. And I can manipulate 2x to get 20x. So 2x is a form of 20x. They have the same degree, at least, a degree of 1. So I can work with that. I'm going to highlight all the other stuff. That's going to be my du, or the parts of my du. So let's actually go through this problem. And as I go through it, all these steps will come together, and it'll be one fluid process the more you practice. So I'm going to define u, u to be x squared plus 3. The next thing you want to do is find the derivative of u with respect to x. That's also known as du dx. So the derivative of u with respect to x. We already established that's 2x. Don't worry about the plus c right now. We're just rewriting our integral. I want to multiply both sides by dx because the goal is to isolate du. Now, you've probably never thought about breaking up dy dx or du dx or anything like that. You probably didn't even know we could do that. We can, however. And I'm going to have du equaling 2x dx. Now, like we already established, we're going to have to manipulate what we have so it looks exactly like what is in the integral. So, if I have 2x dx and I want 20x dx, one quick thing I can do is multiply each side by 10. Because I want to be looking exactly at the same thing. So 10 du equals 20x dx. Now I'm looking at the exact same thing, so I'm highlighting this in yellow. That's what we have in yellow. Now the key with u sub is we are going to take what we have in the original integral and rewrite it completely, or translate it to be all u's. So I'm replacing the x's. The goal is to take this complicated integral and rewrite it as a nice, easy to work with integral. The thing is, everything must be accounted for somehow. You can't just leave anything out. And we're going to be left with a very simple integral integrand then. So I'm going to take this, and what I'm going to do first is rewrite it quickly. So x squared plus 3 to the 9th, 20x. You definitely don't need to do this whenever you get good at this, but this is just so you can see the separation between my u. So I defined x squared plus 3 to be u. And then 20x dx I called 10 du. So I'm going to replace my yellow with 10 du and my pink with u. So let's go ahead and rewrite it. That x squared plus 3 is u to the 9th times 10 du. And now everything is taken care of, everything is accounted for, and now this is going to be a pretty easy integral to take. Properties of integrals, we talked about you could take a constant, pull it out. Hopefully you watched that video before this video. And now you're actually going to take your new temporary integral. So 10 is just along for the ride. I'm going to do the antiderivative of that. That would be adding 1 to my power, dividing by the new power. Now I'm adding my plus c because I'm actually doing my integral. These cancel, and I have u to the 10th plus c. The very last thing you want to do is, because remember, we want to end up again here. We started with x's, so that means you need to go back to x's, so it actually looks like what you want. Almost done. Last thing we have to do is take u and replace it with what we defined u to be, which was x squared plus 3. And there we go. That's the antiderivative. So if you were to take the derivative of this, you would use a chain rule, and you'd get this. All right? So let's do 1 or 2 more depending on time. Here's another example we're going to go through. So I have the integral of x squared times the square root of 5 plus 2x cubed dx. So I'm going to pick out the thing that might be in parentheses with a higher power, a little bit more complicated. This is immediately sticking out at me, and I need to make sure that when I do the derivative of this, a form of its derivative is there. Well, the derivative of this would be 6 or 0 plus 6x squared. That's pretty close to this. I can manipulate it a little bit. So I'm going to go ahead and call u 5 plus 2x cubed. I'm going to do the derivative, which would be 0 plus 6x squared. I'm going to multiply each side by dx, and I get 6x squared dx. Next thing we want to do is make 6x squared dx look like x squared dx. Well, that's a pretty quick manipulation. Let's just divide each side by 6. Same thing as multiplying by 1/6. That cancels. Then I have 1/6 du equals x squared dx. You could leave it as du over 6. It's really up to you. Personal preference. Now what I'm going to do is translate my original integral, and I'm going to write it so that my pink and my yellow are a little bit more separate. I want to get rid of all, oops, not the square root. I want to get rid of all the x's and completely rewrite it with u's. Oh my god, I'm struggling. Here we go. That's better. Now, some of you might be wondering, why aren't you doing the square root with it? And that's a good question. Let's say I called u that whole thing with the square root. Well, if I did the derivative of that, that'd be 1/2 times 5 plus 2x cubed to the negative 1/2 times 6x squared. And there is no way that this looks anything remotely close to what's left over. That would be this would be a square root in the denominator, and I just don't have that here. So this is bad. I don't want to deal with the square root. We're going to leave it because I can do an antiderivative with a square root. So I'm just going to make the u be the thing underneath it. My next job is to take this complicated integrand, or the integral expression, and rewrite it with u's. So I'm going to do the integral of the square root of u, because 5 plus 2x cubed was u, times, I called x squared dx 1/6 du. Now I'm going to take my constant out front so I don't even have to look at it. I'm going to rewrite the square root of u as u to the 1/2. And now I can very easily do the antiderivative of this. 1/6 that's coming along for the ride. I add 1 to my power. Dividing by 3/2 is the same thing as multiplying by 2/3. I'm adding my plus c because this is an indefinite integral. There's no lower and upper constants of integration. And let's just clean this up a little bit. That would be 2 over 18 or 1 over 9 u to the 3/2 plus c. Last thing is I have to go back to x talk. So let's replace u with what I defined u to be, which is 5 plus 2x cubed to the 3/2 plus c. Hooray, we did it. So now let's do one more example. We have just enough time. All right, last example I'm going to do with you. Some trig. I know it's your favorite. So let's look at this and try and pick out u. Remember, when I do the derivative of my u, a form of its derivative needs to be there. If I try taking or calling u secant of x, the derivative of secant is secant tangent, and that's a little bit more than what will be left over if I called u secant. Let's try calling, oh God, what did I just do? Let's try calling u tangent of x. If I call u tangent of x and I do the derivative of tangent, that is secant squared. And look, that's perfect. A form of its derivative is actually there. So let's go ahead and write out the steps here so you can follow along. We're calling u tangent of x. I'm going to do derivative of u with respect to x. Get secant squared x. Du equals secant squared x dx. Oh, look, this is perfect. This is exactly what I have here. I don't need to do any manipulation this time. I don't have to multiply or divide by anything. So all I have to do now is just rewrite my integral in u talk. Tangent of x is u. Secant squared x dx is du. Look how nice that is. And all I have to do is take the antiderivative of u, which would be u squared over 2 plus c, and go back to x's. We always go back to x. You started with x, go back with x. That was a quick one. Okay, your homework for Monday is I have these 6 problems, these wonderful u-sub problems for you. I want you to do the whole process for these. So define u, translate your integral from x's to u's, and then go back to x plus c at the end, something x plus c. I'm going to put up this video here, which is going to have the answers to these problems. However, this is a video, like this one here will be a video from last year, and I basically stopped here. You're going to go all the way and take the antiderivative and go back to x talk. Okay, so check this video out to check your answers, and I will see you Monday. Have a great weekend. Bye.